for this example, right? Like we don't know the mean, so we assume the mean is less than 200, right?
So for this case, we actually do have data. So I just didn't show it. But in this case, we actually performed the test and we found the mean to be 197. So this one we do have the mean.
You do have.
Yeah, but I just didn't show it this. Yeah, because we don't have the data. But
Okay. But is simply solve like a different way to already compare the T and C.
yeah. Yeah, so for this one, so that's kind of the first way to do this. When you do have the data, then you can compute T straight up because you use this formula here to compute T. So since you have the sample mean, you have everything that you need to compute this number here. And so once you compute the T, then you compare that to the C that's in the table. So this is what you look up in the table. And you compare the two. And so since this is less than the C, and we have a left-sided alternative here, then we reject our hypothesis.
We do this with the left side.
Exactly.
With the left side sided, right?
Exactly. Yeah.
And we do a run on the right side of it, so the T must be
Greater than
C.
Exactly. Yeah.
Okay, it's like another way to do the left side and the right side.
Exactly. Yeah. Yeah.
Okay. Thank you so much.
Yeah, it's part of how do you cover the line in such a big house? It does. Six, yes. So I'm shooting like 6 or 7. Basically, yeah, probably like each. So 2 by 2. And we often say it's like much so. It says what it's the I mean, I'm sure that sells out a lot. Yeah. Here's a right. Oh, I did that. I think I'm I just actually. He says that it's pretty. He says like to probably that with this.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good. A little bit gloomy for our final week here, but hopefully it clears up by the end of the week. Okay, so today is going to be the last, I guess, real lecture for this class, and so after today, I don't plan on covering any new content. So today I wanted to just go over hypothesis testing a bit more, and then talk about our final topic with it, which is linear regression. So I did want to go over hypothesis. I've been getting a lot of questions, especially over the weekend, about hypothesis testing. So I want to make sure we go over that again, especially because it's something you're going to need to know for the final. Linear regression is a useful thing to know, but it's very difficult for me to test you on linear regression on the final. And so, we're going to go over how to do it. You've probably done it already in your previous classes, but you know, it's kind of worth reviewing, so you can kind of do that last problem on the homework. But realistically, you know, I can't give you a data set on the exam and expect you to do a regression on that. You know, that's just not practical for an exam. So the linear regression stuff, useful to know in general, but you know, specifically for this class and for the next week, probably not the most important thing that you're in. So I think it makes a good kind of final topic. Just because I can kind of make it longer or shorter depending on how long we talk about hypotheses. Okay. All right. And so besides that, our final exam is going to be a week from today. So it's going to be next Tuesday, May 13th, I believe from 5 to 7. So it's about 2 hours in this classroom here. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay, so I wanted to review hypothesis testing first thing today. Yeah, it's confusing. I think there's just, lots of different terminology, lots of different, the logic is kind of hard to follow a little bit. So definitely, I think worth it to go over it again, just so that, we're all kind of on the same page as you guys are preparing for the final exam. Okay. So the whole idea with hypothesis testing is that, when you're doing your engineering work, a lot of times it's going to depend on the numerical values of certain quantities. And so when you get data, you're going to have hypotheses in terms of what that data is going to be. Okay. And so the first thing to note here is that, when we talk about hypothesis within the context of this class, a hypothesis is an educated guess in terms of the numerical value of a random variable. We'll stop there. So hypothesis is a guess for the value of a random variable. Okay. And the thing that's unique about this is that we're going to have the ability to actually test that and validate that. Okay. So not only are we going to perform a guess for the value of a random variable, we can also perform experiments to verify that as well. Okay. All right, and so there is a systematic process through which we can go through to, test whether hypotheses can be accepted or rejected. Right? And so this process is something that you should follow, whenever you're given a problem to test a hypothesis, this is kind of the step-by-step process that you should follow. Okay? All right, step one. Step one is simply state your hypothesis. Okay? And so for this class, hypothesis will always take the form of some kind of equality statement. So you're going to say that, the value of this random variable is going to be equal to this. Okay? And so what you can say is that, let's say that your random variable is given by X, right? And so this is going to have some numerical value here. So, we'll say X is equal to 24. Okay. Okay, so we have to make some kind of guess in terms of, we have some random variable. We're going to test for it soon. So we haven't tested for it yet, but before we start the test, we have to, give a guess in terms of what the value of that variable is going to be. Okay. Okay. Number two. Probably the most confusing part of this whole thing is to formulate what's called an alternative hypothesis. Okay. Because what you're going to see is that, if in any kind of practical situation, right, you can have a hypothesized value for a phenomenon, but when you actually go out and measure it, it's almost never going to be exactly what you hypothesize, right? Okay. So there's always going to be some discrepancy. So sometimes that discrepancy is really small, sometimes it's large, right? And so the purpose of the alternative hypothesis is to give us some criteria on which we can actually reject our initial hypothesis, okay? Because just because our measured values don't match up to our hypothesis doesn't necessarily mean that we should reject our initial hypothesis. Okay. And so the purpose of the alternative hypothesis is you can think of it as the criteria in which, in which we're going to reject our original hypothesis. Okay. So think of the alternative in that way. And so, we have our original hypothesis. We're going to collect data. The data is not going to match the hypothesis exactly. And so, what are the conditions where we can say like, okay, this data is bad enough where we can reject our original hypothesis. Okay. Okay, and you should know by now that the alternative comes in 3 different flavors. So we have the left-sided alternative, the right-sided alternative, and the two-sided alternative. Okay. Right, and so with the left-sided alternative, in that situation, we are going to reject our original hypothesis if our data is less than our hypothesized value. Okay. I included the term sufficiently there because it's just because you have a mean that's less than your hypothesis doesn't mean that you reject it with the left-sided alternative, because there is a little wiggle room in it. So, there is a little wiggle room in terms of, maybe we didn't measure correctly, maybe there's just some uncertainty. And so not only does it have to be less than the hypothesis, it has to be sufficiently less than the hypothesis. And we'll go over that more. Okay. For the right-sided alternative, we reject if the data is sufficiently greater than the hypothesis. Okay. And then for the two-sided alternative, we're going to check both less than and greater than. And it has to be either sufficiently less than or sufficiently greater than. So with two-sided, you can say that we're kind of doing both. Right. So for a two-sided alternative, you're going to check both sides. Okay. You're going to modify it a little bit. You're going to have your significance level, but essentially you're checking both sides. Okay. Now, which alternative that you choose, ultimately kind of depends on your situation. And so you have to ask yourself, are we in more trouble if our data shows less than? Are we in more trouble if our data is greater than? Or maybe, we need to hit our data on the nose. So maybe we want a two-sided alternative. So, there's no best way there's no best alternative for every situation. It is going to depend. Now, for this class, you know, for the exam and for the homework, obviously, you know, I just told you what alternative to use. But, you know, in reality, this is a decision that you have to make based on the nature of your experiment, based on the nature of your situation. Okay, but for our purposes, you know, I'm just going to tell you, use the left side, use the right side, or use a two-sided. But you know, in reality, you would choose these yourself. Okay. Okay. Any questions on this so far? Okay, good. All right, step 3. All right, step 3, pretty simple step here. We need to choose something called the significance level. Okay. Now, if you look at the previous step, you know, we are only going to reject our hypothesis if our data shows, you know, is sufficiently far away from our hypothesis, right? Because, you know, as with any random event, you know, there's going to be some uncertainty in terms of how we actually measure the data. Okay? So the significance level here gives us a little bit of wiggle room where, you know, we don't flat out reject our hypothesis if we're, you know, if we're less than or greater than. Then this gives us some wiggle room to say, like, okay, we can be a little bit less than or a little bit greater than in order before we really reject our hypothesis. So usually for the significance level, you're going to pick some low value because the significance value tells you a percentage chance that basically, you're basically assigning the probability beforehand that, you know, you may just get bad data. Okay. Because that could be, right? And so, you know, whenever you do an experiment, you're only doing a finite amount of tests. And so in reality, you know, if you have some kind of random event, you know, you should probably test it 1,000,000 times to really make sure, right? And so we kind of talk about the example of flipping a coin, right? And so, you know, if you only flip a coin twice, right, it's very possible that, you know, you get 2 heads or 2 tails. And so in that case, you know, those 2 flips are a poor indication of, you know, the physics of a coin flip, because, you know, intuitively we know that a coin flip should give you a 50% probability of the heads, 50% probability of the tails. Now, if you want to get a perfect 50-50, you probably need to flip a coin 1,000,000 times. And then you're probably going to close to, you know, half in that case. But you know, if you only flip a coin twice, you know, you're probably not going to see a good representation of the data. Or the data is not going to be a good representation of your variable. And so this significance value here gives you a way to kind of say that, you know, it is possible that we're going to have bad tests, and the significance gives us a way out. Okay. Now for your significance level, you know, you're going to choose some low value. Okay. So usually you're going to select something like 0.05 down to 0.01. Okay, so those are probably the 2 most common ones. Because it's a low probability, right? And so, you know, it is possible that you get a bad representation, but generally it's a fairly low probability. Okay. Okay. And then based on your value of alpha here, you know, that's going to tell you how to compute something called your, your f of z value. Okay. All right, and then exactly what you compute here, or what you compute is going to depend based on whether you have a left-sided alternative or a right-sided alternative. Okay, so for a left-sided alternative, okay, so for a left-sided alternative, you're going to compute this quantity called f of z. It should be equal to alpha itself. Okay. And on the right-sided alternative, your f of z is going to be 1 minus alpha. Okay. Now, unfortunately, there's a problem with this though, because the data tables that we're given, don't have all the possible values for f of z. And so what you're going to end up doing is that for a left-sided alternative, instead of computing f of z, you're going to compute f of z is equal to 1 minus alpha, same as the right-sided alternative, okay? And then eventually you're going to multiply that by -1. I should say multiply table value by -1. That'll become clear in a second. So for both the left-sided and right-sided alternative, I think this is something I was a bit confused about I was maybe a bit confusing about last week, just because I hadn't seen the table in a while. But whether you're doing a left-sided alternative or a right-sided alternative, you're both in both cases you're going to compute 1 minus alpha. Okay. It's just that for the left-sided alternative, you have to do an extra step of multiplying by -1 whatever you get from the table. Okay. But in both cases, you're going to need to compute 1 minus alpha. Okay, good. Okay, step 4. So step 4, this is when we're going to look up the table. So this is the table of the t distribution that I sent out to everyone. Okay. And so using the table of the t distribution, we're going to look up our value for capital T. And so, this is the part where, you have your table. And so you have kind of a column for f of z here, maybe 0.5, 0.6, ... 0.95. Okay. So that's the first column. So the first column you're gonna look at is based on whatever value you get for f of z. You're gonna go to that row. Okay. So let's say that we picked a significant value of 0.05. That means the row that we're going to look at the table is the f of z equal to 0.95 row. Okay. And then the other thing you're going to look at here is you're going to look at the column for the number of degrees of freedom. Okay. And remember, the degrees of freedom depend on how many samples that you used. Okay, so whatever the amount of samples that you use, you just subtract -1. So let's say that you ran 20 tests, then your degrees of freedom is going to be 19. That's 20 minus 1. Okay. Okay. And so you go to that column. And then wherever this row and this column intersects, this is going to be your value of capital T. Okay. Okay, and then if you have a left-sided alternative, just multiply this by -1. Okay, so this is the thing that you multiply by -1 for a left-sided alternative. Okay. Okay. All right, so far so good. And then I know I said the alternatives. This is probably the most confusing part. Okay, now that we have our value for t, we need to see, if the data that we get is enough to accept or reject the hypothesis. Okay, so that's kind of the last step here. So step 5 is decide if we accept or reject hypothesis. Okay. So I don't want to confuse you guys a bit more, but I thought of a different way to kind of present this, within the last 20 minutes. And so hopefully this kind of makes things a bit more straightforward, because I know last week when we talked about this, I kind of showed you 2 different ways to approach this part of the analysis here. But I'm going to try to unify both of those into one different way. Okay. So the key to this is going to be this formula here. Okay. So we have t is equal to x bar minus x divided by s divided by square root of n. Okay. So this equation is not changing. The only thing that's going to be changing is how we interpret or how we use this formula. Okay. Okay. So this is the main formula that we're going to use to accept or reject. And let me label everything in this formula here. So this t value here, this is what you're going to look up from the table. So this is what we just did in step 4. So whatever you got from the t distribution table, you're going to plug into that part of the equation there. Okay. N here, of course, this is the number of trials or the number of experiments or number of measurements that we have. S right here, this is the standard deviation of the data. Okay. All right. And then the numerator there, the numerator is the key. So if you look at that numerator is the difference between our sample mean and our hypothesized value. So this x by itself, this x is our hypothesized value from step 1. Okay. So all of that is the same from last week. The only thing that's going to be different here is how we interpret that x bar. Okay. So this x bar, right? Normally this x bar, this represents the sample mean. And so you ran your experiment, you compute the mean, you plug that in here. Okay. What I'm going to do instead is let's solve this equation for this. Because we have everything else, right? So we looked up t from the table, we have our hypothesized value, we have our standard deviation, we have our number of measurements. Let's solve for this. Okay. Okay, so if we solve for this, then what we get is x bar is equal to t times s divided by square root of n plus x. Okay, and so this x bar that we just computed here, this is what I call kind of the beginning or the start of our rejection region for our experiment. Okay? Because whenever you're running an experiment and whenever you're testing a hypothesis, you want to find out if you're going to reject your hypothesis based on the data, right? And so this right here represents the start of the region where, if our data passes this threshold or passes this start point, then we are going to reject our hypothesis. Okay. Okay. And so I think the better way is just to kind of visualize this. And so, if we draw kind of a number line here, and so this is, let's say, x x or x x. So if this is our hypothesized value, okay, and let's say that we are doing a left-sided alternative, okay, and so that x bar there represents the start of the rejection region. And so x bar for a left-sided alternative is always going to be less than the hypothesized value. Okay. So this right here is going to be x bar, the start of our rejection region. Okay. Okay. Because for a left-sided alternative, our t value is always going to be negative. Okay. And so for a left-sided alternative, we're going to reject everything to the left of this threshold here. Okay. Okay. So let's say we ran our experiment. So let's say we run our experiments, we collect our measurements, and we obtain our actual mean, right? So let's say that our mean is right here. So this x hat right here, this is the actual mean from our experimental measurements. Okay. And so in this case, our actual mean is less than our hypothesized value, but it's not quite in the rejection region. Okay. And so in this case, even though our measured mean is less than the hypothesis, it's not enough to reject. Okay. But if our measured mean was within the rejection region, okay, right, and so it's sufficiently less than a hypothesized value, then in this case, we're going to reject. Okay. And when I say accept and reject, what I mean is our original hypothesized value. Okay. So in other words, if you wanted to put this kind of in numbers right here, for a left-sided alternative, okay, if x hat is less than x bar, okay, in other words, measured value or measured mean is less than our threshold, okay, and so in that case, we are going to reject our hypothesis. Okay. So I think with these problems, you're going to spend more time kind of reading the problem and trying to understand what's going on with the rejection regions than you are actually going to do the calculations for the problem. So for your final exam, I actually already wrote this problem for you guys. It's literally only I think 4 lines of work. But I think you're going to spend more time thinking, all right, is it the left side alternative, the right side alternative? What's my t value? So definitely the most difficult part of these problems is the terminology and the logic. So don't get flustered on the exam when you're kind of reading the problem and you're trying to figure out what's going on. You can ask questions, of course, too. But the actual calculations is not that much. And so you're going to see after this, we're going to do an example, one more example, and then you're going to see the actual calculations is small, but figuring out what's going on, that can sometimes take a while. Okay. Okay. Any questions on this? Okay, so let's see what the rejection region looks like for a right-sided alternative. So for a right-sided, okay, so for a right-sided alternative, we have our hypothesized value here. Okay. So for a right-sided alternative, the value of t that you look up in the table is always going to be a positive number. And so that means your rejection region is going to be to the right of your hypothesized value. Okay. So this is going to be x bar, and we're going to reject everything that's out to the right here. All right, and then finally, we have our two-sided alternative. So what's unique about the two-sided is that we have a rejection region on the left and a rejection region on the right. But in that case, we actually bring them a little bit closer to the hypothesized value. So for a two-sided, alternative looks something like this. We have x, right? And we have x bar to the right. We're going to reject everything out here. And then we have x bar to the left, equidistant from the hypothesized value, just like that. Okay. So for two-sided alternative, we're going to check, if it's to the left or to the right. Okay, so this way of doing this is a slight difference from kind of how we learned it last week, where last week, I had you guys compute the sample mean kind of beforehand. In this method here, I'm just going to have you compute the value of x of the threshold first, and then if you have the sample mean, you can see where it lies on this number line right here, right? I think this hopefully kind of unifies kind of both of the examples that we did last week, just because I know they were slightly different in approach, and it's kind of confusing. But with this one approach here, you're just going to look up the value of t from the table, plug into this equation here. And then whatever you get from this equation, that's going to be your threshold for the rejection region. Okay. Any questions on this before we jump into the last example for this? Yes.
So would you still use this if you weren't given data?
Yes. And so if you're given data, then you're going to see where the sample mean actually lands on this number line. So that's kind of what you do after. And so you take the data and you kind of use it at the very end.
Okay, but what would you do if you weren't given data? Like what would be the final answer that you can't compare them?
Exactly. So if you're not given data, the final answer would just be this threshold here. And so this threshold is like
saying what threshold.
Exactly. Yeah. So if you're not given data, said, when you get data, if the data exceeds the threshold, then we reject it. Yeah, good question. Okay. All right. So let's do one last example, and then we'll get on to regression analysis. Oh, shoot. It's incomplete. I might have left the notes up in my office. Okay. We'll make it up on the fly. Okay. Okay, so for this last example here, let's say that we work for a shipping company, and we need to ship pallets or parcels across the ocean. Okay. Okay, so in order to kind of standardize the cost of fuel and the cost of labor to load these parcels onto a ship, there is an upper limit in terms of how much weight each parcel can be. Okay. And let's say that weight, which we'll call W, is 4,500 kilograms. Okay. Okay. Now the thing with these ships is that we're not just shipping one parcel, right? So we're shipping let's say 100 parcels at once. Okay? Okay. And so it's okay, if there are some parcels that are greater than this limit, as long as the total weight of the entire ship is less than 100 times this. Okay. And so what we're going to do is we're going to measure the weight of every single parcel that comes in to the ship, and we're going to see if we're going to use the hypothesis testing to see whether the ship is able to set sail. Okay. 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 So unfortunately, I don't have the actual example that I wanted to do here, but I do remember the hypothesized value was 4,500. So I tried to come up with something to kind of give that a bit of flavor. So so I would definitely check the lecture notes after this. That one has the exact numbers for everything, but hopefully this kind of gives you a bit of context. Okay. So we're going to go through the entire process. We're going to go through pretty quickly because I do want to talk about regression a little bit. Steps 1, 2, 3, 4, and 5. To kind of complete this. Okay. Okay, step 1. So step 1 is to form our hypothesis. And so okay. So our hypothesis in this case is that every single parcel, or the weight of each parcel, is going to be 4,500 kilograms. Okay. And so it's already actually given to us in the problem. Okay. So that's pretty straightforward in this case. Okay. Step 2. Step 2 is to form form the alternative. And so in this particular case, we are in trouble if the average weight of all the parcels is greater than 45 kgs. Okay. And so this would be a situation where we would want to choose a right-sided alternative. Okay. And the reason we choose this is that the ship cannot sail, or the fuel consumption will be too high, or the ship just may sink if the weight is greater than 4,500 kgs. Okay. And so if our data suggests that our weight is greater than 4,500 kgs, then we're going to reject our hypothesis. Okay. Okay. Step 3. Step 3 is for us to choose a significance level. Right. So this is usually pretty standard. And so for this case, we're going to choose 5%. Okay. So we have alpha is going to be 0.05. That means our f of z is equal to 1 minus alpha, which is 0.95. And since we're doing a right-sided alternative, we don't need to multiply by -1. And so whatever we get from the table, we're just going to read that straight up. Okay. Okay. step 4. So step 4 right here, we're going to look up our t distribution for our information here. Okay. Okay, and so let me see if I can pull it up on my phone really quickly. 308, spring. This one. Okay, good. Okay, so for our particular case, with a value for an f of z of 0.95, our degrees of freedom in this case is n minus 1, which is 99. Okay. And so unfortunately, the table doesn't have 99, but does have 100. And so for an f of z of 0.95, we get t is equal to 1.66. Okay. Okay. And so now that we have that t value, we can now go in and whether to accept or reject our hypothesis. But in this case, since we don't have the data yet, we're going to compute the threshold on which, we are going to accept or reject our data. Okay, so we're going to compute our equation from above. So we have x bar is going to be equal to t that we just computed times the standard deviation divided by square root of n plus our original hypothesized value. Okay. Okay. So let's go ahead and plug in for this. And so t we just found out 1.66. Okay. Now, to compute the standard deviation, you do need to get that from your data. And so, unless it's something that's standardized, unless you know it beforehand, you need to compute this from the data. Okay. And you're going to divide that by square root of 100. Okay. And then to that, we're going to multiply by 45, or we're going to add 4,500 kgs. Okay. Okay. So unfortunately, this is kind of how as far as we can get with this problem because I don't have the data to compute that standard deviation for you. But let's fill in something for now. So let's say that from our data we get a standard deviation of about 100 kgs. Okay. And so if we put all this together, and so let me pull out my calculator really quick. Okay. So let's see, 166 divided by square root of 100. Okay. And so that is going to be 16.6 plus 4,500 kgs. Okay. And so that gives us a threshold of 4,516.6 kg. All right. So what this is telling us is that, if our sample mean, so if after we collect all the data, and if the sample mean is greater than this 4,516.6, then we're going to reject our hypothesis and we're going to stop the vote from sampling. Okay. So hopefully that gives you a kind of a more practical example of how to use this, this hypothesis test. Okay. So the idea is, you're going to compute these thresholds and then compare the threshold to the actual measured mean that you get. Okay, and so with that, hopefully this kind of unifies kind of both of our methods, because if you do have the mean, if you do have the sample mean, all you have to do is just check it between this, check it and compare it with this threshold. If you don't have the mean, then this is kind of the upper limit in terms of what the mean can be before we actually start to reject our conclusion or reject our hypothesis. All right, any questions on this? Okay. So like I said, with these problems, it takes longer to kind of figure out what's going on than to actually do the calculations. And so if you look at the calculations we did here, it's very small. And so if you kind of know what you're doing, this is probably going to be the I would say the gimme points on the final exam. It's just make sure that you kind of know what you're doing. Okay. Okay, so for the last 25 minutes today, I do want to review very quickly about linear regression, just because you do have a homework problem on it. I think it's the most fun homework problem, but it's good to kind of review what this is. Okay, so with the linear regression, we're kind of shifting gears a bit. Questions?
How about unknown variance?
Oh, so if you don't have, if the variance is unknown, then what you do is that for this part of the equation right here, you're going to compute the variance from the data itself. Okay. So you're going to have s squared is equal to, I think the formula for that is 1 over n minus 1 summation difference from xi minus x bar quantity squared, where I is equal to 1 to n. And so if the variance is unknown beforehand, you just compute the variance this way, and then you take the square root to get the standard deviation. So yeah, that's the only difference. So there's kind of an extra computation. I'll tell you right now though, because for the exam, it's just really tedious to compute variance. And so this is something I'll give to you on the exam. So I'll give you the variance just so you don't have to compute it, but you're going to treat it as a situation where you don't know the variance. So you'll still use this process, but I'll just compute the variance for you just to save you some time. But yeah, thanks for reminding me. Okay. All right, so let's just very quickly go over linear regression. So the idea with linear regression is to find basically a relationship between two variables in a given experiment or given situation. Okay. So everything that we've done up to this point, the confidence intervals and the random variables and the hypothesis testing, those have all been for single variable analysis. But a lot of times when you're running an experiment or you're doing some kind of engineering measurement, what you're really interested in is the relationship between two different variables. Okay. And so the way to kind of view this relationship is through something called a scatter plot. Okay. Where on one axis of the scatter plot, you're going to have the value of variable 1. Okay. And on the other axis, you're going to have the value of variable 2. Okay. And so basically every time that you perform a measurement, you're going to get a value for both variable 1 and variable 2. Okay. And so what that means is that, each time that you take a measurement, you can put a data point on the scatter plot. And so, let's say that, you perform a measurement and the value for variable 1 is given by, however it lines up on the horizontal axis. And the value for variable 2 will line up for something like that. Okay. And so you're going to perform a lot of these. And eventually you're going to have a lot of data points within the scatter plot. Right, so each individual dot right there is a separate measurement or separate experiment that you ran. And so the idea with regression analysis is to take a scatter plot like this and to try to, determine some kind of relationship between them, okay? So, for this chapter, we're focusing just on linear regression. And so what that means that we're gonna solve for basically a linear line, a straight line, that's gonna best capture the relationship between these data, okay? Okay, so that's the idea. So, probably you guys have seen scatter plots before. So, I'm not going to dwell too much on this, but, think of this as kind of more of a review. And maybe kind of some insights in terms of, what are the exact algorithms that we use to determine these regressions. Okay. Any questions on this so far? Okay. Okay, so there are a couple types of analysis that we can do. Now, what you actually do to determine the trend line in the regression is the same, but it's just a slightly different interpretation of what you're viewing. Okay. Okay, so the first type is called regression analysis. Okay. So in a regression analysis, you're going to make the assumption that one of your variables is not a random variable. Okay, so in other words, it's something that you can control its value very, very strongly in the experiment. And so the control variable, we often call it, well, sometimes we call it the control variable. But another common name for it is we call it the independent variable. So that is one where its value is independent of the value of the other. Right, and then the other variable in this case is the dependent variable. So that one will change and we'll have some uncertainty. Okay, so a good example of this that I've kind of seen a lot of data for is the relationship between age and blood pressure. All right, so there's a lot of hypotheses, or there's a lot of theory in the medical field where blood pressure has some correlation with age. And so generally what people have observed is that as people get older, their blood pressure gets higher. And there is some physiologic background for this, but if you're going to do an analysis on this, in this case, age, this would be your independent variable, right? And your blood pressure here will be the dependent variable. Okay. And so if you were to do a scatter plot, it would look like the following. So, you'd have age on the horizontal axis. Typically, your independent variable will go on the horizontal axis, and then your dependent variable will go on the vertical axis. Okay. Right? Because the hypothesis here is that as you age, or as your age changes, your blood pressure will increase. The relationship doesn't go the other way. So it's not necessarily that if you have high blood pressure right now, you're all of a sudden going to turn 70 years old, right? It doesn't work like that. And so it works the other way. So, as you turn 70 years old, you're more likely to get higher blood pressure. Okay. So this is, I think, a very good example of a regression analysis where one of your variables is independent, the other one is dependent, and you try to form the relationship from the regression. Okay. Okay. Any questions on this? Okay. Okay, so the other type of analysis that you can do is known as a correlation analysis. And so in a correlation analysis, both variables are assumed to be uncertain, and they depend on each other. Okay. And so in a correlation analysis, most of the times when you perform a correlation analysis, you're looking for a relationship. And so you're kind of plotting these two variables against each other, and you're trying to see if there is a relationship between the two. You don't really know that beforehand. So for regression analysis, you're kind of more or less controlling one of the variables, and you kind of know there should be a relationship. But for correlation analysis, it's slightly different. Okay? How you form the trend line, again, is going to be the same between both. It's just, a slightly different interpretation of kind of what you're viewing, and slightly different context in terms of what you're making in the end. Okay. Okay. Good. Okay. So once you've established the type of analysis that you have, that you're going to do, and you've collected your data, right, you're going to have a scatter plot. Okay? Now, the scatter plot is you can think of the scatter plot as just a presentation of the raw data or the raw measurements that you have for both of these variables. Now, a scatter plot by itself, sometimes a scatter plot is easy to visualize, but it's not the easiest thing to kind of describe to someone, right? And so to kind of help with interpreting the data in a scatter plot and to kind of help with communication, oftentimes we like to produce something called a trend line through the data. Okay. All right, so you guys have probably seen trend lines before. So let's say you have a scatter plot and looks something like this. Okay. Right, so we have data that's kind of scattered all around. And so a trend line is basically a single line or a single function that tries to pass through as much of the data as it can. Okay, so for this data, a trend line would look something like that. And so the idea is to kind of, not only, produce something that's easier to visualize, but this trend line, we can actually get a function for that line, right? And so when we determine that function for the trend line, that's going to give us some really interesting information on the data. Because the trend line is just like any linear line that you've learned since algebra, right? And so the trend line is going to look something like this, where y here is the value of your second variable, the variable that's on the vertical axis. X right here, this is the value of your first variable. So that's the value of the variable on your horizontal axis. Okay. Right, so you can see here that this equation represents a relationship between your two variables, okay? And it's because an equation is usually a lot easier to interpret than a scatter plot, okay? But the things that you need to determine on the trend line are m, where m is the slope of your line, okay? And b, of course, this is your y-intercept. Okay, and so variable 2 right there, if you're talking about a pure regression analysis, variable 2, this is your dependent variable. And variable 1 here, this is your independent variable. Okay. Okay, but the whole point of the trend line is to compute slope and to compute the y-intercept. Okay. Okay, so the good thing about modern technology is that there's a lot of software that can compute your trend lines for you. So probably the most common case is to use some kind of spreadsheet program, so like Google Sheets or Microsoft Excel. Okay. So unfortunately, we don't have time to go over the methods in terms of how that happens, but I can give you at least the name of the method. So most spreadsheet programs will use a method called least squares. And basically the idea with least squares is that, they're going to basically optimize or basically, choose the value for the slope and the y-intercept so that the square of the distance between the trend line and each of the data points is minimized. Right. So least squares is a very common technique in math. You might have learned it in a previous math class, but it's used very cleverly here to produce a trend line. Right. Okay, so we're not going to go over the method of least squares, but I at least want to help you interpret interpret the parameters of your trend line. Okay, so because once you have the trend line, examining the slope and examining the y-intercept of the trend line can be very valuable in terms of interpreting the correlation between your two variables. Okay? Okay, so let's start with the slope. Okay, so the slope is probably the most important part. So the slope basically tells you the relationship of, if your independent variable has a certain value, the slope kind of gives you a conversion factor through which, tells you what the dependent variable is going to be. Right? Okay. So the term that I like to use a lot is scaling. And so oftentimes, when you have a value of the independent variable, you can multiply by the slope to see how that independent variable value is going to scale to the value of the dependent variable. Okay. Okay, and then the y-intercept. Y-intercept is actually very interesting. Usually not super helpful, but it can tell you some interesting things about your data as well. So the y-intercept is interesting because, if you think about it in terms of a linear line, this basically tells you the value of the dependent variable when your independent variable is 0. Okay. Now, this has a very important interpretation for your data, because when your independent variable is 0, any non-zero value of the dependent variable we often call bias in the data. Okay. And bias is something that, has a variety of different interpretations. So sometimes it's error. So sometimes if there's significant bias in the data, people might see it as an error in terms of, maybe your measurement device was poorly calibrated when you're doing the experiments. Sometimes it could represent some kind of passive, passive excitation in whatever data set that you're doing. So when you provide no input or the independent variable is 0, if you still get a response, then that might indicate some kind of pre-stress or maybe some kind of, some kind of extra thing that's there that you're not accounting for. So bias is actually very interesting, and in the last 3 minutes we don't have time to talk about it, but it can often be really important when you're looking at your data. But most of the time, for most cases, your bias or your y-intercept is going to be very small or close to 0. And the most telling thing about your trend line is going to be the slope. Okay. Any questions on this? Okay, one last thing I want to talk about here is the quality of the trend line, because not all trend lines are good. Okay. So whenever you produce a trend line, you can assess the quality of the trend line by computing something called the R-squared value. Okay. Because it's not going to be the case every single time that you're going to collect data that's going to be closely correlated. Okay, so there's a big difference, right? And so there's a big difference where if you have your scatter plot look something like this, where all the data points are very closely clustered around a trend line. Right? And so in this case, we can put a trend line through the data like that, and we can see that the data is very closely correlated with the trend. So this is good trend. Okay. But there are other cases where, you have data that kind of, what I call it, I like to call it, I like to call it Chips Ahoy data, where, your data is kind of scattered randomly throughout. So it looks like a Chips Ahoy cookie instead of an actual, piece of data, right? And so sometimes you have data that looks like this, and sometimes people will try, right? So people will try to put a trend line that maybe looks like that, but you can't really say that the second trend line there actually represents any kind of trend at all. It just kind of looks like randomness, right? And so this is called a bad trend line. Okay. And so to assess whether you have a good trend line or not, or whether your data is closely correlated, you can compute something called R squared. Okay. And so for a good trend line, R squared will be something close to 1. Okay. Whereas for a bad trend line, R squared will be maybe like less, like 0.7, something less than that. Okay. Once you kind of get past 0.7, even 0.8, I would say your trend line is probably not that good. You're probably looking at Chips Ahoy data rather than, any kind of real correlation. All right, any final questions before we wrap this up? Okay, all right, and so that is the entirety of EGME 308. And so when we come back on Thursday is just going to be review. And oh, I forgot to mention, so after tonight, I'm going to post a poll on Canvas for you guys to vote in terms of what topics you want to see for the review session, because I'm not going to have enough time to cover everything. And so I want to make sure that I cover the things that people feel most uncomfortable with. So keep an eye out for that poll. I'll send an email out, and then whichever top 2 topics are voted, then we'll cover that on Thursday. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Thanks, Joel. Sure.
So this is where you would stop if you didn't have data.
Exactly.
Okay, just write that statement.
Exactly.
Okay.
Yeah.
Thank you.
Mhm.
No.